Hello friends, this video on structure of atom part 9 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 8. Before we go into the next model, let's understand alpha, beta and gamma and X-rays because this will be needed for the next experiments which Rutherford did. So in 1895, this guy Wilhelm Röntgen showed that when this electron strikes a dense metal, it produced rays which cause fluorescence. There is a metal, when electron comes, strikes this metal, something called X-ray comes out. That time he didn't know what name he should put, so he told it X-ray and the name still continues. Still we use X-ray, right? Because that time he didn't know the name, he was confused what the name should I use, so he called it X-ray and the name is still there. So how he did was that time the electron was there, so he made the electron strike a metal, dense metal, and then he found that some rays are produced, and that rays causes fluorescence in the fluorescent material that is placed outside the cathode ray tube. Please note this guy. If you see, this is an electron, there is a metal, everything is in a tube. This electron is hitting this metal, some rays come and there is some fluorescent material here. You see an impact here. Now he was amazed. How come, man, there's a glass here? How come this rays crossed it? That means there is something great about this rays. And that time he named this rays as X-rays. Correct. And these rays, he did further investigation on the X-rays. He found that this is not deflected by electric or magnetic field. And they have very high penetrating power. They can penetrate to a lot of materials. That's what he found. So he did some research on the rays which he found, and he named the X-ray, and he found that unlike the cathode rays and anode rays which was discovered by that time, these guys are impacted by electrical and magnetic field. If you know, this X-ray was not deflected by electric and magnetic field, and they have high penetrating power. See, it crossed the glass and it impacted the fluorescence material that's placed outside the cathode ray tube. And then they also find that later that certain elements, they emit radiation on their own, and this phenomenon is called radioactivity, and the elements are called radioactive elements. So they are elements which emit rays on their own. You don't need to bombard those elements with electron or something. They just emit on their own. Correct. And there are three kind of rays actually which you will study now: alpha, beta and gamma rays. So X-ray as I covered in this part. Now I'll cover alpha, beta and gamma ray. Alpha rays, alpha particles, I'll call alpha and beta particles and gamma rays. I'll tell you why. Alpha particle is nothing but positively charged helium nuclei. Positively charged helium nuclei. Beta particle is nothing but negatively charged particle and similar to electron. Right? Electron is also beta particle, you can say. And the gamma, if you see, the gammas are rays now, they're not particle. Gamma rays are again like X-rays. They are very high energy radiations, right? And they are neutral, they don't have any charge. And they don't consist of any particle. So if you can see, this is nothing but, you can say, this guy is nothing but cathode rays. And this is anode rays. And this is my X-rays, right? So if you see the difference here is, these cathode rays or alpha particles, they are positively charged helium nuclei and they are deflected by electric and magnetic field. They are positively charged. Beta particles are negatively charged. They are also deflected by electric and magnetic field and they are similar to electrons. And gamma rays are neutral. They are like X-rays. And they don't consist of any particles. And if you talk about the penetration power, alpha particles has least because it has a huge mass. There's a mass involved. Beta particles has little better, and gamma are the best. Gamma, the X-rays, they can penetrate anything. So that's about the alpha particle, beta particles, and gamma rays. Hope you understand the way this gamma rays came, X-ray came. This guy in 1895 bombarded metal with the electron. He found some rays coming up which crossed that tube, the cathode ray tube, right? And there was a fluorescent material nearby, it impacted that. And he found that there's something called X-rays, which is not having any charge, and it is very high penetrating power. And there's something called alpha and beta particles. Alpha particles are positively charged helium nuclei, and beta are negatively charged particles similar to electron. So why we study this is because there's a guy called Rutherford, and he did an experiment to prove that the Thomson model is incorrect. So what he did was, and it's a very famous experiment, he used a very thin gold foil and he bombarded that with the alpha particles. So if you see what he has done is, there was a gold foil here, the alpha particle, that is He plus 2. This guy he bombarded this guy with on this gold coil, and he found that most of this alpha particles went straight, few of them reflected, and few of them deflected. Please note, most came straight, few deflected, and very few reflected. So if you see, most of the alpha particles, these are all alpha particles, right? It went straight because, and only some got deflected or reflected, and some bounced back, very few bounced back. Now he observed something from this. That is, some bounced back and most of them went just crossed it. That means there are a lot of empty space. Because you see, if 90% of this alpha particle is going straight, that 90% is coming here, that means most of the thing is empty space, right? The place which I'm hitting is empty space, correct? And with that, he concluded that this guy, in an atom, the nuclei is very small, which has the mass, and is very dense because some of the particles got bounced back, right? It's very dense, but most of these is empty space. That's what he concluded from this experiment, right? He used this junk sulfide, and there's nothing but a phosphorus kind of thing, which will flicker or glow when the alpha particles strike it, so that he can understand and can know where the alpha particles coming out. So with this experiment, if you see, he concluded that, yeah, I'm hitting the electron. If you take one electron now, I'm hitting this with alpha particles, and most of the alpha particle is going, right? Most of it is going back. Only one came back out of 100. That means there's something which is there and is very dense, right? And other places all empty space. That's what he concluded with the experiment. It's a very, very, very critical experiment for chemistry and very famous experiment. So the conclusion from this experiment was most of the space in the atom is empty. If you see why, because 99% of the alpha particles just went straight. That means most of the space is empty because the alpha particles, most of them are undeflected. And a few of the alpha particles got reflected and few came back, right? That means there must be very dense thing here. And also, since my alpha particle is positively charged, since it came back, this guy is also positive charge. This guy is also positive charge. That's why it deflected. If it was negative charge, it would have contracted here, right? It would have stuck to this. But this guy bounced back. That means that guy is also positive charge. And that is very dense. So that means he concluded that the positive charge is concentrated in a very small volume, and that repelled and deflected alpha particles. Correct? Also, he did all the calculations about the number of alpha particles came straight, number of alpha particles deflected. He found that the nuclei occupy a very small volume as compared to the whole volume of atom, right? If the radius of atom is 10 to the power 9 meter, the radius of nuclei is 10 to the power minus 15 meter. And that's what he say. If we have a cricket ball as a nuclei, then we have an atom of diameter 5 kilometer. That is the amount of empty space we have in atom. This thing was concluded from Rutherford experiment. Thus, Rutherford gave an atom model. He told that the positive charge and most of the mass is in a very small region, this region. And this region was called nuclei. Rutherford gave the word called nuclei, that this region is called nuclei. And he told a negative, this nuclei is surrounded by electrons that move around the nucleus in a very high speed, just move around. That was Rutherford explanation, but that was incorrect. I'll tell you, the electron part here is incorrect. He told that electron moves around here in a circle orbit. There's an orbit. In this orbit, the electron moves. There's so many orbits, he told. In this orbit actually, it moves around in a orbits. And he told this is similar to what we have solar system. We have a sun and we have so many orbits and all these planets moves around, right? Similar to that, he told, we have our atom model. Atom looks like similar to our solar system, where the electrons moves around in orbit and we have a very dense thing called sun here. Here we have dense thing called nuclei, right? And he told that the way this electrons and this nuclei are held together is by the power of attraction, electrostatic force of attraction. But we'll see that this part and this part is incorrect. This part is correct actually. Today also this part is correct. But these two parts were proved to be incorrect in the later release.
Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.